questions here. So next, we're going to go directly to Bob DeMajistre, who will talk about the ENA science and its measurements and its rates. Bob, take it away, please.
Okay, can you hear me?
Yes.
Okay, great. First slide, please. Okay, so I am going to first go over really quickly what ENA imaging is and the processes involved, noting that it is a remote sensing technique, which is somewhat different than the in situ measurements that have been described before today. Then I'll go through the measurement objectives and the instrumentation that will allow us to make the measurements that we need to make. Next slide, please. Okay, so first I wanted to talk about charge exchange in the context of ENA imaging. This is really the fundamental process that drives a lot of the physics of what we're measuring and how we're measuring it. Next slide, or next whatever. The charge exchange, first off, is the source of pickup ions in the solar wind, which we will eventually measure in the heliosheath. What's happening is that the solar wind will charge exchange with cold neutrals, pick them up in the plasma frame. These are energetic in the plasma frame, so this is a source of energetic atoms in the solar wind. It also serves as a drag effect on the solar wind, which you've seen earlier in Drew's presentation. Next, please. So once the plasma gets out into the heliosheath, the charge exchange, it sort of makes the plasma into a sort of leaky boat. The energetic plasma charge exchange with the cold neutrals replace these, and the energy is lost to the plasma from the plasma. And this happens on a very predictable time scale, and as the process becomes less efficient, the plasma, the hot portion of the plasma remains for much longer. And next slide, or next. And this is essentially what we see. The plasma that's losing these hot ions as atoms glows in ENA, and this is what we catch in our cameras and use for imagery. On the scales that we're talking about, these neutral atoms travel in almost straight lines because they're not affected by the magnetic field, and the gravity and light pressure are almost negligible in the energy ranges that we're looking at. And I should mention that what we're really seeing is the non-thermal plasma when we image the heliosheath in these ENAs. That is the pickup ions, which originated in solar wind, whatever is shock accelerated, etc. Okay, the next slide, please. Okay, we already have measurements of ENAs from the inner heliosphere from both Ibex and Cassini-Inca. And soon we will have IMAP, which will provide more resolution, better energy coverage, better overall measurements, all of this from 1 AU. Next slide, please. However, looking at this system from 1 AU, a lot of ambiguities will remain because we are making a line of sight measurement from what is essentially the sun looking outward at an object that we're inside of. So it will be very difficult to know where along the line of sight these where these ENAs are coming from, and consequently the overall shape of the object that we're looking at. Next slide, please. So that leads into the first of the objectives that we're answering with ENA imaging. The central question, the first question for the interstellar probe is the idea of force balance and how the heliosphere is really formed with the balance of the solar wind and the local interstellar medium. And this balance is manifested in the shape of the heliosphere, and that is one of the central measurements that we're trying to make with the ENA imaging. And added to that is how this changes as solar activity modulates this system. And this is just a picture of the STM and the science traceability matrix. This is extracted right from there. Next slide, please. One more. There you go. Okay. So what we hope to get is an external view of the heliosphere and heliosheath. That is the primary measurement for this objective. And again, it is to measure the shape, and looking at multiple energies will allow us to really distinguish both the shape and the processes that we're looking at. And again, I'll draw your attention to the lower right, where we see that that the higher energy plasma is going to emit ENAs much more slowly. And what that does is it allows us to see farther from the termination shock. So at the low energies, we'll see a lot of ENAs closer to the termination shock, giving us a real detailed view of what's going on in that near shock area. Whereas at the higher energies, what we'll be seeing is the plasma farther away and deeper down into the tail to give us a nice picture of the larger shape. Now, what this will require is a very large dynamic range, and what you see in the lower left is on top an ion spectra built from Ibex and Inca and the Voyagers in the heliosheath, and underneath it the corresponding ENA spectrum in the heliosheath. And what you see is that we need to cover 5 or 6 orders of magnitude in intensity for these ENAs. Next slide. We're also, the Ibex ribbon and belt are also targets for this. I don't think I need to go through very much of what this ribbon and belt are. It's a circular structure, not a great circle that Ibex was surprised to see during the first few months of the mission. And it started out as a peak and became a ribbon and a circle. And at higher energies, Inca saw a similar thing. Again, an enhancement. but it has a slightly different shape. And what we've seen with Ibex is that as we approach the Inca energies, those two shapes merge. Next slide. Okay, our primary observation for this will be on the way out. There are maybe a dozen mechanisms that have been proposed for this ribbon. There are, two or three that have become popular in the community, but we still don't know which mechanism really is what's building the ribbon. We don't know whether the ribbon and the belt are the same structure even. What we have not been able to make a whole lot of progress at 1AU. There have been distance measurements and that sort of thing, though again, not unambiguous. But as we fly out and look at this object from 20, 50, 70 AU, we should be able to unambiguously figure out where it is and make progress on what the individual mechanisms are that make this thing look like it does. And just to follow up on Drew's presentation, what we'll get from the ENA imaging for the ribbon is really a preview early on. We will know where it is and what the mechanisms are, but the in situ measurements will really drive what we understand about the physics. None of the mechanisms that have been proposed so far close in terms of the plasma physics. There are a bunch of unknowns, and the in situ measurements will really should be the measurements that close that close the science on that. Okay, next slide. Okay, we're talking about instrument requirements to make these two sets of measurements. Right off, we have the large energy range that is from 1 to 100 keV. This is driven by the global imaging, allowing us to see both solar wind energies and back towards the tail. Next slide. The angular resolution at 5 degrees is driven by ribbon and belt observations. This is what we've seen in the Ibex and Inca data as the highest resolution, the highest or the smallest scale spatial structure that we expect to see here. Next. The dynamic range is really driven by the large energy range that is needed from the global for the global imaging. Next slide. What we do have is a long time to make these measurements. The integration time is really based on the change of the field of the change of the field of view that's going to happen, and that's going to happen over weeks and months. So we'll be able to integrate for a long time. And what this does is it shifts the priority from the effective area of the instrument to the signal to noise, since we can afford to integrate for weeks on end. Next slide. One more. Okay. We can go to here. In the interest of time, we have two types of instruments that can make good portions of these measurements. On the left, you see an IMAP Ultra type of instrument, which is which is a later version of the Inca instrument. And on the right, you see an IMAP High type of instrument that is the follow-on from Ibex High. On the left, the Ultra instrument is a true imager. And on the right, the IMAP High instrument is a single pixel camera that does very nice spatial resolution at the 1 to 10 keV energy range. Next slide. What we really want to do is fly both of these. That would give us the coverage over the full energy range at high resolution for the ribbon and the belt. What we need to do this with the IMAP High type of instrument is have an actuator to move it over the whole field of regard. The drawback here is that that's a lot of mass for two instruments and a lot of mass for the actuator. And in addition, the actuator will be a disturbance to the attitude, which needs to be compensated for. Next slide. We could just fly IMAP High. It would save us the mass. However, we would still need the actuator, and we would need to figure out how to get from 15 to 100 keV, which is not available in the current IMAP High energy range. And we'd still have the attitude disturbance from the actuator. Next slide. Again, we could fly an Ultra with two heads, there would be no more moving parts and have the full field of view, although we would have limited sensitivity below 5 keV, which is where the ribbon really is, and the spatial resolution will not be as good for this. Next. However, this is the option that we've chosen for the example payload. And because mostly it gives us most of what we want, and it is kind of a proof that we can do this. Next slide, please. I think Alice is going to talk about the accommodation. So I'm not going to go over this in the interest of time. Next slide. As far as technology development goes, for the Ultra style instrument, what we'd want to do is go down to lower energies, possibly thinner foils with UV rejection, along with UV rejection with that. And we may be able to do some sort of collimation scheme to increase the resolution, but that's TBD. We could also extend the IMAP High instrument with a lightweight balanced scan platform and redesign it for a higher energy range. Next slide. I think that's the last one. And I'll just leave this up here. So we have a plan to do ENA imaging of the global imagery of the global imagery of the heliosheath and the ribbon. And we have instruments that can be built to do this. And I will stop right there.
And again, right on the second. Boy, you guys are doing really well. Hey, so thank you very much. Fantastic, very succinct and very clear presentation, and very honest on the trades here. Made it very clear to me, at least. So let me just remind the panelists here. Please follow along in the chat for the panelists, because we're trying to sort of divide up questions for this afternoon's discussion. So for those of you on the panel, if you haven't looked at the chat, take a look at the chat. I'm trying to divvy up some questions for you. Okay, so that brings us to 12 o'clock, and that brings us to lunch, at least here on the East Coast. So we will now have a lunch break for 30 minutes, and we will reconvene at 12:30 promptly, and then we'll have Jamie to talk about the dust analyzer. Thank you, and see you then.